Good morning, all. So, in this session, we are discussing about the implementation of the SR latch using the logic gates. Latch and flip flop are made with logic gates, and logic gates itself doesn't have any memory. And these are the some of the logic gates: AND or NOT, NAND and NOR, and these two are called the universal gates. Logic gates itself does not have any memory, but using the feedback from output to input side of the logic gates, they can be used for storing the one bit of information. So in this fashion, we need to interconnect these logic gates. Then these logic gates can acquire the capability of storing the one bit of information. So here I took the two NOR gates, which are labeled as 1 and 2. Their outputs are interconnected like this. Means NOR gate 1 output acting as the one of the input to the NOR gate 2, and NOR gate 2 output acting as the one of the input for the NOR gate 1. The second inputs for the each NOR gate are labeled as one is S, next one is the R. And the latch or flip flop have the two outputs, and the two outputs are values are complement with each other. So here for time being, I labeled the outputs as the A and B, and inputs I labeled it as the S, R. And to understand the functionality of this SR latch, we should be familiar with the truth table of this NOR gate. And just by observing this truth table, we can conclude that to the NOR gate, if one of the input is 1, output becomes 0. If both the inputs are zeros, output becomes 1. You remember, or you keep this point, you keep this point in your mind. So based on that, we can estimate the what are the output values of this SR latch. So here initially I took S is equal to 1 and R is equal to 0. This NOR gate, one of the input is 1, output is 0. Here value is 0. This output is feedback to the NOR gate 2. Okay, means both the inputs are 0 0. Its output is becomes 1. So here 1, here 0. The next combination is the S is equal to 1 and R is equal to 0. S is equal to 1 and R is equal to 0. Okay, S is equal to 1 and R is equal to 0. So you know that when S is equal to 1, okay, what is the output of the NOR gate? It becomes 0. This 0 is connected to the one of the input of this NOR gate 2. When both the inputs are zeros, what is the output value? Output value is equal to 1. And third case is the S is equal to 0 and R is equal to 1, right? The same explanation for the third case also. Next one is the both values are zeros. S is equal to 0 and R is equal to 0. So in this case, to estimate the output values, okay, we need to consider the present output values. Initially assume Q is equal to 0 and Q bar equal to 1. Q is equal to 0 and Q bar is equal to 1, right? So this 0 is connected to this this input. So 0, so here also 0, both are zeros, output becomes 1, and this 1 is connected to one input of the second NOR gate, then its output becomes 0, right? And the last case is S1 and R1. S1 and R1. This NOR gate output becomes 0. This NOR gate output also becomes 0. Why? Because we know that in the NOR gate, if one of the input is 1, output becomes 0. And all the input combinations and their output values I consolidated in a table. That table we are calling it as the truth table, right? S0, R0. Okay, the next state is same as the present state. S0 and R1, next state is equal to 0. S1, R0, next state equal to 1. S1 and R1, okay, and it is the forbidden state. Why this state is the forbidden? For this input combination, both the outputs of the NAND gates are either 0 zeros or 0 1. This is the invalid case, or and this input combination is the forbidden, right? We never operate this SR latch for S is equal to 1 and R equal to 1 when we implemented SR latch using the NOR logic. Okay, this is the corresponding symbol of the SR latch. Okay, this is the logic diagram and this is the corresponding symbol, right? And we can also implement the SR latch using the NAND gates, right? This is the logic diagram and this is the corresponding truth table. And you know the basic functionality of the NAND gate. As per the basic functionality of the NAND gate, if one of the input of the NAND gate is 0, output becomes 1, right? So here S is equal to 0, R is equal to 1, right? One of the input of this NAND gate is 0. What is the output value? 1. So this 1 is feedback to the second NAND gate. So both values are 1 1. Output becomes 0, right? Next combination is the 1 0. Here 1, here 0. If one of the input is 0, what is the output value? 1. And both the inputs are 1, what is the output value? 0. Next combination is S is equal to 1 and R is equal to 1. To estimate their output values, first we need to consider the what are the present output values. So initially I assuming the present output values as Q is equal to 0 and Q dash is equal to 1. And based on that, there S is equal to 1 and R equal to 1. So here Q is equal to 0. There is a feedback to the NAND gate 2 input, right? One of the input is 0. What is the output value? 1. This 1 is connected to the one input of the NAND gate 1, right? This 1 here also 1. Both the inputs are 1 1. Output becomes 0, right? So likewise, I consolidated the all the values in a tabular form. This table I am calling it as the truth table. This truth table is going to illustrate the functionality of the this SR latch, which is built using the NAND gates. Okay, I am consolidating S0 and R0. Both the outputs of the SR latch are same, means 1 1. This is the forbidden. S0 and R equal to 1. Next state, okay, next state is equal to 1. S1 R0, next state is equal to 0. S1 and R1, next state is same as the present state. SR latch, until now we discussed about the SR latch. So in that, the output simply follows the input changes, but there is no control. Okay, and to get more control over the SR latch, okay, we made certain modification. The modified version of the SR latch, we are calling it as the gated SR latch. The difference is, so here we added one control signal to this SR latch by adding this control signal. So here we are calling it as the enable. Okay, enable. This becomes the gated SR latch. So this is the symbol of the gated SR latch and the respective logic diagram of the gated SR latch. Okay, so through this arrangement we can get more control over the functionality of the this gated SR latch. Okay, so here when enable equal to 1, then only the input values of SR are connected to the S dash and R dash. When enable equal to 0, irrespective of the SR values changes, okay, when enable equal to 0, whatever may be the values of SR, S dash and R dash receives the 0 0. And you know, when S dash 0 and R dash is equal to 0, next state is same as the present state. Next state values same as the present state, and the corresponding values are consolidated in a truth table, right? When enable equal to 0, irrespective of S and R values, okay, next state is equal to present state. When enable equal to 1, okay, both the inputs of S are 0 0, next state is present state, right? Enable is 1 0 1, next state equal to 0, next input combination 1 0, okay, its next state is equal to 1 1 1, and this is the forbidden. We never operate this SR gated SR latch for the input combination of S is equal to 1 and R is equal to 1. Next, so here we implemented gated SR latch. Okay, so here I added the AND gates instead of AND gates, I want to implement, okay, this gated SR latch using the NAND gates. So this is the logic diagram of the gated SR latch, which is implemented using the NAND gates.